when you were talking about the upper limitation, you said it's x is the upper limit of integration because x squared is greater than x?
Yeah, I saw that typo and I was going to fix it, and then I forgot. Yeah.
And it just, I heard what you said and that made sense, it just didn't seem like it was the same as what was written there.
Yeah, I meant to fix that. Yeah, so this is page 2. Should be x squared is less than or equal to x.
School 1.
Oh, yeah. Alright. And yes, I'm keeping track of these for bonus purposes. Okay, so this evaluated the limits, x squared, the lower limit, and x, the upper limit, dx. So now we're going to plug in x for y, and then we'll plug in x squared for y. So we'll have 8x minus x squared minus x squared over 2 minus 8x squared minus x cubed minus x to the 4th over 2. So now everything is in terms of x. So now we just have a single integral to evaluate. So that's going to be x to the 4th over 2 plus x cubed minus 19 halves x squared plus, plus 8x. So then we just finish this off in the usual way. 10 plus x to the 4 minus 19, 6 x cubed plus 4x squared, evaluated at 0 and 1. So then you just plug in your limits and you're done. 71 over 60. All right. So any questions about the, can be classified as either type 1 or type 2. Generally, there are going to be regions that have a shape, something like this. You could look at it either way. So here we have y being a function of x, y equals 0, x equals 0, and then here, wherever these cross, we'll just call this x equals b. So here's a type 1, but we can take the same region and classify it as type 2. So for type 2, we want constant boundaries in terms of y. So I'll draw, let's make these axes straight for a change. Okay, so same region. So constant boundaries in terms of y. So it's y equals 0, and then wherever this intersection occurs, call that y equals a, and then we'll still have x equals 0 as a lower limit in x, but now the upper limit is going to be x equals what? Just in general, so we just have a general function f of x here. So how would we write the upper limit in x? The limits in y have to stay constant. So for that portion of the boundary, how can we write x in terms of y? Let me be more concrete. This example of such a region that actually looks kind of like this would be x equals 0, y equals 0, x equal pi over 2, y is cosine of x. So alternatively, you get x equals 0, something here, y equals 0, up to y equals 1. So how are we going to describe this?
Square root of y.
No? it's described by y equals cosine x, but if we want to say x is equal to something.
Could you just say 1 minus the cosine of x?
No?
What area is it that you're looking for?
Yes, inverse cosine. You got to use the inverse function. So whatever describes this, y is a function of x, use the inverse function, describe x as a function of y. So, if you're having to integrate a function over a region like this, so let's just call this region D as usual. So double integral of whatever integrand you have can be written either as the integral from 0 to pi over 2 in x, and then 0 to cosine x, y. So the inner integral is respect to y. So this is the type 1 way. Or 0 to 1 in y, 0 to inverse cosine x, cosine y rather, in x, f of xy dx dy.
Now, what is it that the inverse cosine describes?
It describes this portion of the boundary of a region. So it's the exact same curve. We're just using different equations to describe it.
Okay, right,
Yeah.
okay.
Yeah.
I was reading that as y equals the arc cosine of x, which is why I was confused
Oh,
about why
yeah.
they describe the same line, but that makes sense.
Yeah. Well, that reminds me of how they normally teach you how to find inverse functions, because they tell you velocity is a function of mass, or you're going to call velocity v and mass m. Now you need the inverse function. Are you really going to switch? Okay. All right. Now, so in some cases, it doesn't really matter which point of view you use. You can do whatever is more convenient. But what could happen, depending on what function you're integrating, you may have to switch from one representation to the other just to be able to work it out. So here's an example where you're given a region described one way, but you have to switch to the other. Because ultimately, you're going to anti-differentiate this function with respect to x or y. Then you'll have a new integral with these limits plugged in. What if the function that you get is something you just don't know how to do? So it's even worse than a Zinger problem. So e to the y cubed. Integrate over region D, where D is x goes from 0 to 1. And y goes from the square root of x to 1. So let's draw that. Okay, so here's a graph of the square root of x. So it's this region right here. Okay. So here we have y square root of x, y equals 1, x equals 0. Okay, so obviously this is not the scale. X equals 1. All right, so now you can go ahead and try to work this out. So this is going to be integral from 0 to 1 in x, that's your outer integral. Then your inner integral is going to be square root of x to 1, and you'll fill in e to the y cubed dy. Looks simple enough, but don't try integrating or anti-differentiating e to the y cubed. It will never happen. So, let's try changing the description of a region to see if we get something that we can do. So, what that means is we need constant boundaries in terms of y. Well, this region extends from y equals 0 to y equals 1. So we have our limits in y.